So we're very happy to have our very own Egor Shelukhin from University of Montreal to tell us about Lagrangian configurations and Hamiltonian maps.
Thank you very much. I'm very glad to speak here and to see you all. I do see the cameras, and I also hope to see the chat. So please, if you have any questions, write on chat. But if I don't see the chat, please somebody tell me that there's a question. Thank you. Okay, so I will talk about joint work with Leonid Poltorovich. This is about, after all, the group of Hamiltonian diffeomorphisms Ham M omega of a closed symplectic manifold M omega. And to start with, let me define a displaceable set. So a set, a closed, let's say, subset of M is displaceable if there is a Hamiltonian diffeomorphism that displaces it from itself. And there is an old question of Poltorovich regarding displaceability, and let me both state and motivate it. So we heard about this question and its solution a few weeks ago from Mac, Chokyu Mac, but I would like to repeat it. So consider the two sphere, let's say the two sphere of total area 1, and consider two circles on this sphere that are disjoint, and divide the sphere into three pieces, two caps of equal area B, and an annulus of area C, which is in this case 1 minus 2B. Then if 2B is bigger than 1/2, otherwise B is bigger than a quarter, then the union of these two circles, which I will denote by bold math L0 sub 2B. Sorry, it's a little bit of kind of complicated notation, but it's going to be helpful later. So this union is non-displaceable just by area reasons. By the way, if the caps were of different areas, it would be displaceable. So that's why they have the same area. And similarly, that's why B is sufficiently large. However, this union is stably displaceable. So it means that once you cross this union with the zero section in T star of S1, it becomes displaceable. Basically because there is a loop of Hamiltonian diffeomorphisms that somehow is contractible, which is kind of the double rotation. And it is non-zero on both components. So the suspension displaces. And then, so the question is it true that, well, instead of crossing with zero section, we can cross in equator in S2 of some area? And so the question is it L0 to B cross the equator, which we'll call just L to B? So this notation will appear later. I'd like to make it now. So is it true that this L to B is non-displaceable when A is small, this area of extra factor? And Malk and Smith in 2019 proved the following fantastic result, that it is indeed non-displaceable if A is sufficiently small relative to B. So if A is less than 3B minus 1. And 3B minus 1 is actually B minus C, because C is 1 minus 2B. So I made this calculation. Okay, and so an open question that still remains is to find the best possible A given a configuration. So is it really 3B minus 1, the optimal one, or maybe something bigger? Okay, and the key idea of the proof of Mack and Smith is the following. Well, so L2B is the joint union of two components, two Lagrangian tori. So L0 to B and L1 to B. Okay, and it becomes rigid, somehow more rigid in the symmetric square of MA, where MA is this manifold S2 times S2 twice A. So the twice A is the small spheres. And so more specifically, you can take the just cross product of L0 to B and L1 to B. This cross product by itself is a Lagrangian submanifold of MA squared, so MA times MA, but it is also disjoint from diagonal. So we can look at its projection in the symmetric square. Okay, so it will be sitting inside the smooth locus of the symmetric square. So you get this Lagrangian torus L curly to B in the symmetric square. Yeah, so the symmetric square here is just, it's MA squared over Z2, where Z2 acts by interchanging the coordinates. Yeah, so XY goes to YX. And you consider it as an orbifold. Okay, so the diagonal is somewhat singular. Okay, and so this L curly to be inside the symmetric product is rigid because there are more holomorphic disks with boundary on L to B that one has. And basically, so such holomorphic disks are constructed from branched covers of the disk by by a Riemann surface with boundary. So kind of we took sigma going to disk with a holomorphic map pi. It's a branched cover, and we require it to be of degree 2. This degree 2 corresponds to the second symmetric product, symmetric square. All right, and okay, we require it also to have two boundary components. And then a holomorphic map from this Riemann surface to our manifold MA that sends the boundary components to Lagrangian tori yields exactly such a disk, right? And the way it does is that we write the formula. Well, we have the projection pi from sigma to the disk, so we take a point on the disk. We can take its pre-image, it's a subset in sigma, generically with two elements, sometimes with one element, which we kind of think of, two elements except that they're the same, right? And then we can evaluate our map nu on this pre-image, and it gives us a well-defined element in the symmetric product. And this can be reversed. And in fact, so there is a certain correspondence, the tautological correspondence between these two kinds of maps. And perhaps the key example is that the annulus can be presented as a branch cover of the disk of degree 2 with two branch points. Because we can think of the annulus as, the annulus between two circles of radius r and 1 over r. And then the disk, we can think of it as the quotient of this annulus by, z goes to 1 over z. And precisely you see that, 1 and minus 1 are the branch points. Right. And then these disks allow us new bulk deformations by, so to say, truly orbifold classes in the framework of Choen-Podder and Fukaya or Otto and on. And in this way, it turns out that this extra freedom of choosing new bulk deformations allows us to allows Mack and Smith to produce non-vanishing Floer homology of this Lagrangian 8 torus L2B, well, with some bulk and some bounding Cauchy. And in particular, it implies that L curly 2B is non-displaceable by orbifold Hamiltonian isotopes. And so L2B in MA initially is non-displaceable by usual Hamiltonian isotopes. Because somehow, if you have a usual Hamiltonian diffeomorphism of MA, then it acts on MA times MA by kind of its square, yeah, so kind of phi times phi, and that is symmetric, so it passes on to the symmetric product. Okay, and so if L2B is displaceable by phi, clearly L curly 2B will be displaceable by this symmetric square of phi. Okay, and then next part of the story is Lagrangian spectral invariants. So to my knowledge, they first appeared in work of Viterbo, and they were later investigated by Leclerc and Sapolsky and Fukayo, Otto, and Ono, and by many others. Well, so what I want to say is just a brief description. So let's take a Hamiltonian on a symplectic manifold. And let's suppose we have a Lagrangian submanifold L of the symplectic manifold with non-vanishing Floer homology. Then to this we can associate a real number, so the spectral invariant of the here fundamental class, but it can be any other class, as long as it's somehow non-zero. And so this satisfies certain good properties, in particular the following holes. So intuitively it calculates the smallest action level under which one L appears. This kind of unit appears in the Floer homology of L with itself, as calculated by means of the Hamiltonian. Okay. And second of all, it's called the spectral invariant because actually it's not only in the reals, but it's in fact in the spectrum of H relative to L. So it means that it's somehow an action of a generator. So it's a symplectic action of a chord from L to itself with a capping, right? So kind of a contraction to L. And finally, so under certain technical conditions, so basically you want all the periods and relative periods of omega to be rational. So then if H restricted to L is a constant, that kind of depends on, in this case, it just depends on nothing, it's just a constant, then this spectral invariant actually equals this constant. And I wrote here a fundamental class because that's how I usually write, but I prefer here to write just unit to make it less ambiguous. Okay, so and what we do is we investigate Hamiltonian metric rigidity and dynamics by means of spectral invariance coming from this curly L2B and its generalizations LKB in the kth symmetric product. And this LKB is similar, except that somehow in this, so to say, potato, you have many circles which are kind of level sets of height function instead of just two. And you again stabilize it by equator in S2 to A, right? And then you have this 2K torus L curly KB in the K symmetric product of MA. Okay, so here K symmetric product is MA to power K over the action of the symmetric group on k elements. Okay, and which level sets I will specify just a little bit later. Okay, so in this way, given a Hamiltonian on MA, which is a 4-manifold, we obtain a spectral invariant of this Hamiltonian, which is indeed a spectral invariant of LKB relative to a fundamental class, with the bulk deformation and boundary and bounding cochain that one finds. And we take it relative to the symmetric kth power or symmetric sum, kth sum, I don't know, of this Hamiltonian. So kind of this HK evaluate on set x1 until xk, so to say, in the symmetric product is the sum hx1 until hxk, and indeed it is kind of invariant on the action of symmetric group, so it's a well-defined thing. And we normalized by 1 over k, because here we had somehow k summons, and then we normalize by k to keep Hofer norm, so to say, controlled. I will talk about this a little bit more in just a moment. Okay, and another way to think about this is that Gambodo and Gis and others have studied the Hamiltonian group of a surface by its action on the configuration space of, let's say, k points on the surface. And what we do is we realize a certain Floer theoretical version of this. Right? In particular, for a surface, one can think of the symmetric kth product as a certain compactification of the configuration space. Okay. And so since we have a Floer theoretical version, we get results on Hofer metric instead of hydrodynamic metrics that can measure LP norms of the vector field. Of course, we have Hofer metric, which is a remarkable bi-invariant metric on the Hamiltonian group, which is given by this formula. But I must say that it basically means that we take the C0 norm on the Lie group of the Hamiltonian, on the Lie algebra of the Hamiltonian group, which is identified with smooth functions of 0 mean. And on right, so this gives us an invariant Finsler structure in the Hamiltonian group, and we can take the length of a path from phi to psi, and then take the infimum of such length. So that defines us a metric, right? So kind of, and indeed, integral from 0 to 1 maximum absolute value ht dt is the way to measure a length of a path. And what is really remarkable is that this metric is non-degenerate because, in particular, by Eliashberg and Polterovich, it is false for LP instead of L infinity, so to say. Now, a general open question about the Hamiltonian group with the Hofer metric is whether its diameter is infinite or not. And we know it in many cases by now, but in general, it is open. What we do know in complete generality is that the version of Hofer metric on the universal cover of the Hamiltonian group is indeed of infinite diameter for all M omega closed. This is an argument of Ostrover. However, in this case, we don't know that this pseudometric d tilde on the universal cover Ham tilde is non-degenerate. So we know it in some cases, but we don't know it in general. Okay, and so using these spectral invariants that I have described, we obtain certain results in two-dimensional case and also in four-dimensional case. So let me start with the two-dimensional case, right? So the case of surfaces. In this case, we know that the diameter of the Hofer metric is infinite. So for surfaces of genus 1 and higher, this is a result of Lalonde-Magda from 95. And in the case of S2, this is a result of Polterovich from 98. And okay, so diameter is infinite. So we might ask which groups actually embed there in a rigid way. And here by rigid, I will focus on two particular definitions. So let's take a group G with a bi-invariant metric D. So for us, G will be just somehow abelian. So we don't worry too much about it. And we have a morphism of groups from this G to Ham, right? And so it can be isometric, which means just that the distances are preserved. And it can be quasi-isometric, which means that, well, maybe the distances aren't precisely preserved, but they are up to a multiplicative factor and an additive somehow error. Okay. All right, and for surfaces of genus at least one, we have plenty of results. So we know that Rk with any norm embeds quasi-isometrically into Ham. We know that R infinity with L infinity metric embeds quasi-isometrically to Ham. And even more, we just know that the smooth functions with compact support on an open interval with, you know, just the sup norm, the C0 norm embeds isometrically into Ham of sigma. Okay, so this follows from Polterovich's original argument that works in the case of S2, but it also works by work of Zapolsky that uses Lagrangian spectral invariants. And the idea here is to take let's say a simple non-separating curve on our surface. I drew a torus, pretty how should I say, impressionistically. And and then we can foliate a neighborhood of this curve by curves of a similar type. And then we can apply symplectic rigidity to functions that are constant along each curve. So, and there are different flavors of symplectic rigidity. One can, you know, apply energy capacity inequality in the universal cover, or one can apply boundary depth of the Floer complex, or one can indeed apply Lagrangian spectral invariance, or, you know, stable non-displaceability. Okay, and so I must also say that these results 1, 2, 3 that I mentioned here extend to other classes of manifolds. However, for S2, except for the quasi-isometric embedding of R into Ham of S2, that follows from Leonid's 98 paper, not much was known until recently, and so just to make a to give a normalization, let me describe this embedding here into Ham of S2 as follows. So we take the equator, we take a smooth version of the characteristic function of the equator. We adjust it a little bit so that it has zero mean, but still has C0 norm 1 and still is equal to 1 on the equator. And then, so the Hofer distance of the time t flow of this autonomous Hamiltonian, you know, will be a distance actually just t from the identity. So in fact, it's an isometric embedding. And so this has motivated the question of Kapovich and Polterovich from 2006, which asks, you know, is the whole Hamiltonian group contained in an R tube around this R? So in other words, is it true that Ham of S2 is quasi-isometric to R? And quite recently, by two different works, the answer turned out to be no. With Poltravich, we prove that, in fact, the C-infinity functions with compact support in an open interval with sup norm embeds isometrically into Hamiltonian with Hofer metric. So clearly no. So yeah. One can take a look, for example, at the asymptotic cone of Hamiltonian, or anyway, you just have many other directions. And so independently and simultaneously and using different techniques, Cristofaro Gardiner, Humilier, and Seyfadini also proved that the answer is no, because they proved that Rk for all k embeds quasi-isometrically into Hamiltonian with Hofer metric. Okay. Moreover, one can prove that for all open sets in S2, let's say just a kind of a proper open set, no matter how small, such an isometric embedding can be chosen to have support in this open ball. In fact, one can have it be a subgroup of the kernel of the Calabi homomorphism on this little open set. And this is some sort of a small scale rigidity in Hofer's geometry. So it's kind of small geometric scale, but large Hofer scale. Okay, and the same result for Rk for all k was also proven by CGHS. So Cristofaro Gardiner, Humilier, and Seyfadini. All right. Okay. Another two-dimensional result is the following. So again, CGHS proved in 2020 the following fantastic result, that the group G of homeomorphisms of disk with that preserve the area, and one takes the connected component and one of course takes the compactly supported ones. So this group is not simple. And recently CGHS have extended this result to the identity component of the group of homeomorphisms of S2 preserving area. So the case of S2. And shortly thereafter, we have realized that our spectral invariants also give information about these questions. So to formulate our result, let me say a little bit more about the proof of these two theorems. So to prove that something is non-simple, one must present a proper normal subgroup. And in this case, one can take the group of homeomorphisms introduced by O and Müller, but it is more efficient to take the group of finite energy homeomorphisms, namely those homeomorphisms that can be C0 approximated by Hamiltonian diffeomorphisms, all of which sit inside a certain ball in Hofer's metric around the identity. And so CGHS prove that the group G over the group GF, which is a normal subgroup, so they prove that R embeds in this quotient. So then definitely these two groups are not the same. Okay, and what we were able to prove is in our spectral invariance that in fact quite large linear space embeds into the quotient. So we prove that C1 functions on half-open interval over the bounded C1 functions on the same half-open interval. So this embeds into the quotient. So somehow G is very non-simple. Okay, so these are the results in two dimensions. And so now there are also a few results in 4 dimensions. So in 4 dimensions, recall that somehow we were talking about stabilization. So we had something happening on S2, and we wanted the same thing to keep on happening once we cross S2 with S2 of small area. One thing one might hope for is that the map from Ham of S2 to Ham of S2 times S2 small area to A, that sends phi times identity, so kind of stabilizing Hamiltonian diffeomorphisms. One can hope that there is some sort of isometric embedding or maybe quasi-isometric. Of course, it is a Lipschitz map, so it is kind of, in fact, it decreases the lengths. So there's a chance for both of these both of these questions to have a positive answer. And we don't know how to prove this. However, we can go somewhat towards this direction. So we can prove that our embedding of this large linear space into Ham of S2 does stabilize from the point of view of Hofer metric. So to kind of on this flat, we do indeed get a quasi-isometric embedding. Okay, so kind of our embedding composed with the stabilization is still rigid from point of view of metrics. Okay, and you see it is quasi-isometric instead of isometric because in Ham of this stabilized manifold there are non-trivial, non-contractible loops. So there's an exotic element in pi1 due to Gromov. And so this quasi-isometric here comes from dealing with this loop in pi1. And on the level of universal covers, this is indeed an isometry. So yes. So this asks how large is A with respect to area of S2? A is really pretty small. Okay, one has to quantify it carefully, but it is somehow very small. Okay, so it's the same. So somewhere here I had this condition that A is less than 3B minus 1. And so somehow we take B, well, B, we take B bigger than 1/6. So A is something. Okay, so actually, so it's a calculation that I have made during the proof. So yes, the original sphere has size 1, and yes, and so somehow we take the B that corresponds to being of height less than 1/6. So B is bigger than 1/2 minus 1/6. So that's 1/3. So you see somehow when B is very close to 1/6, then A is really close, really small. But if B is a bit bigger, then we can take also A a bit bigger. But in any case, A is smaller than 1/2. Okay, so it really depends. For example, yeah. And another thing I must say is that in this quasi-isometric embedding, the quasi-isometric constant, this error constant, the multiplicative one, depends on how small A is. Okay. So if it's really, really small, then this constant, so kind of the smaller the A is, the worse this constant is. But on universal covers, when we don't care about these loops, it is indeed an isometry. Okay. And okay, I will make further comments about this in a moment. But now I'd like to talk about yet another question in 4 dimensions, which is that of Lagrangian packing, which is a seemingly unrelated question. So we take a Lagrangian in M that is indeed displaceable. So one can pack at least 2 disjoint copies of this Lagrangian in M. And so then the question is how many Hamiltonian copies of this L one can pack. So is 2 the best? Maybe 3, and so on and so on. So how many Hamiltonian copies of L, so phi1 L until phi k of L, can be pairwise disjoint? Yeah. So that is the question. And a closely related question is that of Lagrangian Poincare recurrence. So where we fix a Hamiltonian diffeomorphism and ask how often L comes back to itself, at least in the from perspective of beginning to intersect itself under this time kind of discrete time dynamical system. Yeah. So in other words, how often phi I L intersect L is a non-empty set. In dimension 2, this follows from area arguments that the frequency is area of the smallest disk that L bounds over area of M. Okay. Of course, L is displaceable, so it bounds the disk. And so for recurrence, the conjecture is that for all closed L and for all closed phi, there should be a positive lower bound on this frequency. And so a result of Ginzburg and Gurel proves this for all L in CPN, but for a particular class of Hamiltonian diffeomorphisms that are rigid, that are Hamiltonian pseudorotations of CPN. Yeah, so the ones that have the set of periodic points being exactly n+1 of all periods. And we provide certain first cases of examples of a Lagrangian that works for all phi. Okay, so more precisely, we prove a packing statement from which we deduce a recurrence statement. So the packing statement is the following, and here I will specify exactly the necessary A. So suppose that L in S2 is a boundary of a cap of area, let's say B, between 1 over k plus 1 and 1 over k. Okay, and suppose that S in S2 is the equator, right? And also let's say that A is small, so it's k plus 1b minus 1 over k minus 1. So if k is 2, it's actually exactly 3b minus 1 that we had before. And so our claim is that, of course, one can pack MA by k copies of this Lagrangian, because even in S2, one can pack it by k copies, yeah, because its area is 1 over k, smaller than 1 over k. But we claim that one cannot pack MA by k plus 1 copies of this lambda, which is also true in S2, of course, by area reasons, but one cannot pack also MA by k plus 1 copies. Okay, so this is a packing statement, and from which you can deduce a recurrence statement, namely that the lower density of the set of return times, so I, such that phi of I lambda intersects lambda, is at least 1 over k. And this is MA. Okay. And theorem about packing, so theorem E, implies theorem F by a certain combinatorial statement, which you somehow immediately think is obvious. Then you realize that it's maybe not so obvious, and then after 2 days you realize that it's actually not so difficult. Okay, but what I must say is that it is actually important for the recurrence statement that it's a fixed Hamiltonian diffeomorphism. Okay, it's not just a sequence of Hamiltonian diffeomorphisms, because this gives a certain kind of time translation invariance of the problem, which is very useful. Yes, because you want to intersect with lambda, which is kind of the time zero Lagrange. Okay, so these are the four-dimensional results. And now just a little bit about the method of proof. Of course, if there are questions, I'm very happy to answer questions.
Well, what would be the analog of theorem F if you wanted to use several Hamiltonians?
So the intuitive analog would be just replace phi upper IL by phi lower IL, where phi lower I is just any sequence, yeah. And that would actually be false, because you can, let's imagine that L can be packed 3 times at least, yeah. So then you have L, phi1L, phi2L, but then you can have phi3 equal to phi1. So it's going to be phi1, phi2, phi1, phi2, phi1, phi2, and it's never going to intersect the initial one. So kind of that version just doesn't work.
If you allow for any arbitrary sequence, but theoretically you could imagine that maybe you could impose conditions on the sequence, like for example powers, so then it's true, but
yes, absolutely. So actually, I think that it's just somehow what one should measure for an arbitrary sequence is not quite this lower density, but a certain other type of lower density.
So, I mean, people consider in dynamics actions of groups. You have, I don't know, your favorite finitely generated group attacks. And so then you can address the question about recurrence with respect to balls in word metric in the group. And to the best of my understanding, there are results like this, so we simply did not address it. Yeah, so even I think for a billion group, it could be non-trivial.
Thanks.
Yes, so somehow what we do in the case of Z. Yeah. Yes. Okay. So now just a little bit about the method of proof. And here I will specify the particular configurations of Lagrangians that we use. So we will study Lagrangian estimators, which are certain type of Lagrangian spectral invariants that are supported on these joint Lagrangians. But so what are precisely these joint Lagrangians? So we look at the level sets of the height function. Actually, it's sort of a normalized height function that takes values in -1/2, 1/2. So it's kind of the moment map for standard S1 action. And we take the level sets in such a way that they, let's say we have K level sets, and we have 2 caps of equal areas B, and K-1 annuli of area C, also equal area C. Okay, and of course we want total area to be 1, so 2B plus K-C is 1. And also we require that B is bigger than C. In fact, if we work on the sphere, we can even take B equal to C, and then B is equal to C equal to 1 over K plus 1. But for the 4-dimensional case, we really need B bigger than C. And so we suppose it. Okay, so kind of L0KB will be the union of these height sets in S2. And LKB will be the stabilization by the equator in the small sphere. So this is a subset of MA, which is S2 times S2 of area twice A. Okay. All right, and so we prove that if A is between 0 and B minus C, and K is 2 or bigger, so at least 2, and also for technical reasons, we ask A, B, and C to be rational numbers. So in this case, there exist maps mu KB from Ham tilde of MA to R, certain spectral invariants that satisfy a list of properties, including the following. For all phi and psi in Ham tilde, the following holds. So these maps are Hofer-Lipschitz. So mu KB of phi minus mu KB of psi is less than Hofer pseudometric between phi and psi. Yeah, they satisfy what's called Lagrangian control. So this is a version of function being constant on Lagrangian, implying that the spectral invariant is constant. But in this situation, it means that if HT restricted to the jth component of LKB is a constant, or maybe constant depending on time, but only on time, then mu KB of the the element that HT generates in the universal cover. So let's say that H is mean normalized here. So mu KB of this flow is the average of these constants. If they depend on time, we also take the average over time. Furthermore, these maps are conjugation invariant. They are also positively homogeneous. So mu KB of phi to the m is m times mu KB of phi. M is a positive integer. They satisfy the Calabi property. So if H is supported, for all times in an open set U that is disjoint from LKB, then mu KB of its flow is proportional to the Calabi invariant of this map. And finally, if a Hamiltonian H is given as F plus 0, so with respect to the splitting of MA into S2 and S2 twice A. Yeah, so it depends kind of only on the S2 coordinate of area 1. Then mu KB of phi H, in fact, depends only on the time 1 map of the Hamiltonian flow of F in Ham S2. Okay. So we use these properties as well as the freedom to choose B and K. So we can make K as large as we want, and we can vary B. We can almost always we can take it pretty close to 1/2, and we can always vary it. Yeah. So we use this to prove our results. And so just the construction of this mu KB involves the spectral invariance from before, but we homogenize them. Yeah, so we take the limit of 1 over m CKB of the mth iterate of H. Okay, and it turns out that for almost all results, this homogenized version is most useful because of the positive homogeneity property and the conjugation invariance property, as well as the Lagrangian control, of course. But I might comment later that actually for C0 results, it is the CKB itself that is more useful. And CKB does not have these properties 3 and 4, but it has some other properties that are more useful for C0 questions. Okay, so now once we have these invariants, let me sketch part of the proofs of our results. So let me first sketch the proof of the existence of isometric flats inside Ham S2. Yeah, so we want to prove that C infinity functions on closed interval, okay, with compound support embeds isometrically into Ham S2. So instead of just smooth functions in an interval, let me instead consider even functions on a symmetric interval. So let's take F to be H composed with Z. So Z is the height function in the sphere. And so let me suppose that h is an even function on minus 1, 6, 1, 6. Okay, so this is exactly that normalization that that condition that I was talking about earlier. Right? Okay, so then we can always extend it to have zero mean without changing the C0 norm, because we can, for example, we can just kind of reflect it in a certain way. And so it is enough to prove that the Hofer distance between the diffeomorphism phi1f and identity is the C0 norm of H. This is just kind of bioinvariance property of Hofer metric, and obvious bioinvariance property of C0 norm. Yes, is there a question? Okay. So if there's no question, so by changing signs if necessary, we can suppose that the C0 norm of H is attained at some point x0 in the interval minus 1, 6, 1, 6. But we can also say that this x0 is positive. And then for a suitable B, well, actually, we need to take a sequence of BI rational that converges to B, but okay, fine, that's kind of not a problem. So for this suitable B, mu 2B of phi1f, by the Lagrangian control property, is exactly evaluate H at this x0, which is exactly the C0 norm of H. So mu 2B of phi1f is H norm C0. But so I rewrite it here. But on the other hand, mu 2B of phi1f is Hofer-Lipschitz. So it is less than d Hofer phi1f identity. But d Hofer phi1f identity is clearly less than the C0 norm of H, because this particular f is one way to generate phi1f. So just by definition. And so, we get exactly what we want. We get the Hofer distance between phi1f and identity is the C0 norm of H. Okay, so that's the proof. And so now a little bit about the stabilization and small geometric scale embeddings. So for stabilization, proof is similar, but we have to to prove the result on the level of Ham of MA, as opposed to the universal cover, we want to treat the effect of Gromov's exotic loop and pi1 Ham MA. This is done by comparing the Lagrangian estimators to a certain quasimorphism on the group Ham MA that was introduced by Strover. And I must also say that this Gromov's exotic loop was studied by Magdaf and Abreu Magdaf in many different publications. Okay, and about the result on small geometric scale embeddings, the result is well, the proof is similar, but instead of mu 2b, we use mu kb for k large enough, so that to say the topmost, let's say, circle in the Lagrangian configuration sits inside a little ball. Little ball, let's say cap of area 1 over k, and that sits inside U. And of course, we use conjugation invariance to put a particular cap inside U. Yeah, U can be something. Okay, and finally, so I talked about how to deduce recurrence from packing, but I did not say anything yet about how to prove packing, and this is what I'd like to do now. So instead of the Hofer pseudo normer, Hofer's pseudo distance from element of universal cover to identity, let us consider its homogenized version. So let's define d bar of phi to be, the limit 1 over m d tilde phi m identity. Okay, so this is asymptotic Hofer norm. And now by homogeneity and the Hofer-Lipschitz property, we have that mu kb of phi is still a lower bound for this homogenized version, which is, of course, so homogenized version is smaller in general than the than the non-homogenized version, but this is still a lower bound. Okay. Okay. Yes. Okay. So this d bar is the same as this d bar. Okay. So and then what can we do? So we had our Lagrangian, that is stabilization of the boundary of a little cap of area B between 1 over k plus 1 and 1 over k. Okay. So our lambda was this cap times the equator in the small sphere. Not, is there a question? Okay. Claude, is there a question? Okay, so right. So now what we can do is we can take the characteristic function of this Lagrangian, which we can obtain as the product of the characteristic functions of L, of this boundary of the cap, and the equator. Then we want the smoothing of it, which we can obtain as the product of the smoothings. Yeah. So. And we can always arrange the smoothings to be contained in arbitrarily small neighborhood of lambda, of L times the equator. And we can modify them to have zero mean by still keeping the C0 norm of F to be 1. This is this smoothing. And still F is 1 on lambda, and still it is supported in an arbitrarily small neighborhood of lambda. And then by the property that F restrict to lambda is identically 1, we get that mu kb of phi f is 1 over k by Lagrangian control. And this 1 over k comes exactly from the fact that we average the values over the configuration. So it is 1 here and 0 on all others, so it's 1 over k. But of course, as I said before, this is a lower bound for the asymptotic Hofer norm. Okay, so this is part 1. But part 2 is that if lambda can indeed be k plus 1 packed, let's denote L k plus 1. Then by Sikorov's trick, for delta being so for F being supported really close to lambda, we have that d bar of phi F is actually at most 1 over L. So, if L is k plus 1, this cannot be. So this proves the result. And so just to remind Sikorov's trick, it works as follows. So if F is, if lambda is L packable and F is supported really close to lambda, then by these packings we can redistribute F to L different places. So we have L different copies of F, so F1 until Fl. They have disjoint supports. Okay, and since they have disjoint supports, the C0 norm of their sum is actually 1. Okay? So it means that the Hofer distance of the product of their time t flows from identity is at most t. This is on one hand. But on the other hand, this redistribution from point of view of Hofer distance does not cost that much. It costs only something, only at most a constant that depends on L, but not on T. Okay, so therefore we get that 1 over LT distance of phi LT F to identity is at most, 1 over LT, T plus constant depending on L. So it is 1 over L plus something that goes to 0 as T goes to infinity. Okay. So this is the proof of Sikhorov's trick. Okay, so I think this is time to finish the talk. I had some technical comments which I can comment upon later, but for now, thank you very much for your attention.
Thank you. Questions?
Can I ask a question? I'd like to. Sorry. Yeah. So I wonder about this Lagrangian Poincaré recurrence. How general can one expect this to be? I mean, are there sort of obvious cases where it doesn't happen? Or?
Well, okay. So of course, so a classical statement is that if instead of Hamiltonian map you have symplectic map, right? Then the statement just fails, because you can take torus and meridian and just So and I think there are no counterexamples known to the Hamiltonian version of Lagrangian Poincaré recurrence. So the actual Lagrangian Poincaré recurrence.
That's what our son was calling.
Okay, so the only examples where it's known is your case and the one of Bashak and Victor.
Yes, so, and so I think there is no manifold known yet for which it is known for all L and all phi. So you see, somehow Bashak and Victor prove for CPN for all Lagrangians, but for particular Hamiltonian diffeos, and we prove for this MA for a particular Lagrangian and for all Hamiltonian diffeos.
Okay, thanks.
Can I ask one? Could you say a little bit more about those? You mentioned situations where you might not want to homogenize your subspectral numbers, and in context of some C0 results. Could you detail a little bit more?
Yes. So let me make it. Okay. So you see, the homogenized spectral invariants are they're okay. Non-homogenized and homogenized spectral invariants satisfy the Lagrangian control property. However, the homogenized ones are homogeneous and they are conjugation invariant. But the non-homogenized ones are not homogeneous and not conjugation invariant, because basically you can kind of move around the Lagrangian, yes, by conjugation. So that's makes it not true. However, they are subadditive, and also they are partially additive, which is actually not known and probably not true for mu KB. But okay, at least not known. Okay. And in fact, and also they are partially additive. So if H is supported in U, which is disjoint from LKB, then the just CKB, okay, on S2 will be additive. And using this, one can one can prove that tau KB, which is CKB minus some CK prime B prime, it is actually advantageous to take K prime equal to 1 and B prime equal to 1/2. So this is kind of the honest Lagrangian equator in S2. And so one can prove that this is C0 continuous. and Hofer-Lipschitz, and in fact, it's also subadditive up to finite error. So it's like quasi-subadditive. And so the C0 continuity here, the proof of the C0 continuity here uses a lemma of Cristoforo Gardiner, Umilier, and Seyfadini about so that connects C0 smallness, Hofer metric, and support of a diffeomorphism. Basically, it kind of shows that if it is C0 small, then you can somehow recombine it into something that is supported in this U that is disjoint from LKB, paying only a little bit of Hofer energy. So this is proven by fragmentation techniques. Okay. And well, and then so since you asked, let me prove something. So you take this tau KB, and let's say that you evaluate this tau KB on a Hamiltonian that is somehow supported in the upper. Let's say that it is it is continuous and it can kind of explode. Yeah, but because of C0 continuity, it is you can still play this tau KB on that thing. Yeah, and when K goes to infinity, in fact, this tau KB tends to, just by somehow Riemann integral formula, yeah, to integral of this function from B to 1/2. So it kind of, from the equator to wherever B takes you. Yeah. Okay, and then and then this means that if the kind of, so to say, the Hamiltonian homeomorphism generated by this guy is finite energy, then the primitive function of this H must be bounded. Okay, and so this is the main part, and then you use this quasi-subadditivity to kind of prove something about the quotient.
Cool, thank you. More questions?
Can you briefly repeat which results you get from working only in S2, and for which ones you must go to S2 cross S2? Or always?
Yes. So the answer to this question is very simple, but I will still repeat. But the answer is that all results in 2 dimension you can prove only working with S2, and results in 4 dimensions you must go to S2 times. So more specifically, the result on Hofer flats in Ham of S2 you can prove working only in S2, and the results on C0 topology you can work only in S2, and I will make a little bit of a comment about this in just a sec. And so in the 4-dimensional results you really must use S2 times S2 2A, so the 4-dimensional thing. So in particular, the stabilization of the flats and the and the Lagrangian packing and Lagrangian Poincaré recurrence. Of course, Lagrangian packing and Lagrangian Poincaré recurrence for S2 is standard, and in fact, even stronger results hold just by ergodic theories. Okay, but one thing that I wanted to mention about working strictly in S2 is that if you work strictly in S2, you are not bound by the condition that B is strictly bigger than C. So in fact, you can actually take B equal to C, and in this case, all the areas of the complement are 1 over K plus 1. All the areas of the connected components of the complement are 1 over K plus 1. So it is some sort of like a limiting case. And in this case, on functions of height, our spectral invariants agree with PFH spectral invariants that are that appear in work of CJHS. Okay, and so one might very naturally expect that these two invariants are, very closely related. Presumably the same, but okay, after choosing normalizations a little.
Mm.
And this seems really, really very plausible. So, there are various intuitions that somehow related to perhaps something like Hegardt-Floer homology. Okay.
Thank you. Well, since I'm unmuted, can you further comment on these subgroups, on this interlacing of normal subgroups or something? Can you explain how the normal subgroup of Dan, Vincent, and Sobhan fits into your picture? So it's just like the graph of 1 over x among your functions smoothened off, or how is this?
Yes. So the function of Dan, Sobhan, and Vincent is you take this h to be okay. I should say correctly. You take it to be positive and convex, and well, depending on normalization, either of positive derivative or negative derivative. So maybe in my picture it's actually negative derivative, but okay. And you require it to have an infinite integral, which is of course positive, but you require it to be infinite. And so in our case, we have this additional parameter b, which is kind of the area of the cap. So we are able to prove somehow that the primitive function is must be bounded. Rather than its value at 0, so to say, or at 1/2, depending on how you like. Yes, and this exactly agrees with this kind of limiting case picture, right? Because in this limiting case, it's kind of a particular value of b.
Okay, any more questions? Then we can thank the speaker again.